everyone. This presentation is about SmartBlock, a visual programming language and its programming environment for Internet of Things. Internet of Things refers to devices or systems that connects over the Internet for communication and exchanging of data. These devices are embedded with sensors, software, and other technologies. IoT applications enable end users to remotely control home devices from their smartphones and automate everyday tasks. SmartThings is one of the most popular open IoT platforms for home automation, and it supports various IoT devices. Apps under this platform, called Smart Apps, are written in Groovy programming language. Using a visual programming language makes it easy for users to develop programs by dragging and dropping program elements graphically. It eliminates the barriers to complex programming tasks in text-based programming, allowing even inexperienced programmers to write programs. Visual programming is also applicable to programming IoT applications for home automation. This study has designed a visual block language called SmartBlock built on the SmartThings platform to automate devices at home. SmartBlock is aimed to overcome the three usual limitations of visual programming. These are expressiveness, extensibility, and error prevention. First, visual language tools are good for simple programming, but they have limited expressiveness when it comes to writing large IoT applications for home automation. Second, visual language tools should provide a method for writing the parts of IoT application code that are not expressible by the tools. This method will bridge the gap between simple but less expressive visual programming and complex but more expressive code-based programming. Third, inexperienced users can produce error-prone IoT applications, such as commanding two conflicting actions or an infinite loop of actions. Because users are not professional developers, visual language tools should provide error prevention methods to help users identify their mistakes. Internet of Things automation calculus is the standard for evaluating the expressiveness of a visual programming language and was used to evaluate SmartBlock. SmartBlock was used to build 54 of the 56 sample smart apps in the SmartThings Groovy IDE. To adapt it for the development of smart apps, SmartBlock is extended to have preferences for constructing installation pages and smart device configuration, as well as event condition action or ECA rules for specifying tasks. Integrity of ECA programs is guaranteed by checking for redundancy, inconsistency, and circularity in the ECA rules before the code generation. The authors implemented the SmartBlock language in its programming environment with Blockly, a client-side JavaScript library that can be used for creating visual block languages and environments. Custom blocks were designed using Blockly Developer Tool, and a code generator was implemented. This code generator translates custom blocks into Groovy code. A connected event, condition, and action block was designed to represent the ECA rule. An event action block, also called as EA block, was also designed where the condition part is assumed to be true. Figure 8 shows the two connected ECA blocks where the first block represents an ECA rule that when a door is unlocked and if the user is present at home, the smart app turns on the light and plays music. The second rule means that when the door is unlocked and if the user is not at home, the smart app sounds a siren and sends a push message to alert that there is a stranger in the house. Events are obtained from smart devices, and there are two types of events. These are device events and abstract events. Device events are triggered by smart devices, such as sensors, while abstract events are triggered by events such as timers, app touches, and mode changes in SmartThings. Attributes of these events are filled in the whole of the blocks as shown in Figure 9. Device events indicate device status changes, such as from unlock state to lock state of the door in Figure 9. The timer event at 8 a.m. every weekday from Monday to Friday is an abstract event. The installation and updating event blocks invoke the predefined callbox, installed, and update in the predefined callbox section. Condition block represents Boolean expressions regarding the state of devices, input variables, and constants. Figure 10 shows the three condition blocks. The condition for checking device states represent a conditional expression that checks whether the value of the device sensor present sensor 1 is present. Next is a comparison expression that is true if the number of occurrences of the event active from the motion sensor 1 during the last 3 minutes is greater than 1. Lastly, this compound block represents a conjunction of the given two condition blocks. An action block represents an action to be performed. Figure 11 shows some sample action blocks. The first action block represents a smart device command to turn light 1 on. The second one is a SmartThings API call to send a push message. The third example shows two action blocks combined to represent a sequence of actions. Action blocks are also designed to store intermediate values of SmartThings state variables. The fourth example shows how a variable box1 is defined and increase its value by 1. Lastly, this action block is a timer for processing another ECA rule in 3 minutes. The IoT calculus was extended with device groups and aggregation. With this, a custom block for a group of devices was designed. Figure 12 shows a group of devices sharing a common attribute. Users may write ECA rules that conflicts with one or more ECA rules. These conflicts are redundancy, inconsistency, and circularity. The activation of a device more than once is a sign of redundancy. It is shown in Figure 13. Inconsistency leads to two conflicting actions on the same device, as shown in Figure 14. Circularity leads to an infinite loop of events and actions. It is shown in Figure 15. For conflict analysis on visual ECA block programs, the analysis method needs to know the dependencies between the ECA rules. To figure out event flows between the ECA rules, the method first determines which actions trigger which events, and then constructs an event flow graph or EFG of the ECA rules. During the construction of the EFG, an ECA rule with multiple actions is decomposed into a set of ECA rules with one action each. ECA rules are redundant when there are duplicate actions in the reachable actions E of each event E. Reachable actions from a given event can be obtained by computing the transitive closure of the EFG. Based on the conflicting action information, the method finds the inconsistencies by computing all the reachable actions for each event E. If there are both an action A and its conflicting action denoted by A' in reachable actions E of the same event, then an inconsistency is present. The analysis method detects cycles in the event flow graph by using Tariant's strongly connected components algorithm. The environment provides three functions. These are visual block programming, compilation of SmartBlock into smart apps, and conflict analysis. Figure 16 shows a workspace that consists of tools for rule, preferences, and code. Users develop a smart app by dragging and dropping ECA blocks, event blocks, condition blocks, and action blocks onto the workspace on the right. After building ECA blocks for a smart app, the code tool generates an abstract syntax tree, or AST, for the ECA blocks, analyzes the AST, and generates groovy code for the smart app. Figure 18 shows this compilation process. The AST for the ECA blocks is shown in Figure 19. Figure 20 shows a complete code generation example compiled from the two ECA blocks in Figure 8. The AST of each ECA block compiles to an event handler method, referencing the event, condition, and action nodes in the AST. We can see the two event handlers in the generated code. The code tool generates groovy code for a smart app by composing the definition, preferences, predefined callback, and event handler sections according to algorithm 1. First, the code generator in the tool makes up a definition section using the smart app name, author, namespace, description, and icon URL. The code generator then produces an installation page from the blocks in the preferences tool. When the users do not write anything, this will be the default code generated for the installation page. The code generator writes input methods for setting up the smart devices based on the information extracted from the AST of the smart app. It collects the devices that appear in the event nodes and generates an event section to declare inputs for all the collected devices. It repeats the same procedure for the condition and action nodes to generate a condition section and an action section. For example, the three sections in the preferences thus generated are shown in Figure 20. After the Groovy codes for the smart apps are generated, the codes can be published and installed through the SmartThings Groovy IDE. Users can then use the smart apps on their mobile devices. Figure 21 shows an overview of our implementation of SmartBlock based on Blockly. A supporting compiler for SmartBlock comprises an AST constructor, analyzer, and code generator. An AST constructor is developed to interface with the visual blocks written in JavaScript generated by the Blockly developer tool and produce an intermediate AST. The analyzer implements the conflict analysis methods explained. The code generator implements the proposed algorithm. Figure 22 shows the internal design of an ECA block, which has three value input blocks for the event, condition, and action. Once we build a custom block, the Blockly developer tool provides its definition code written in JavaScript. Figure 23 shows the definition code of an ECA block that appends the event, condition, and action blocks as value inputs, checks the types, and appends the fields. The authors implemented the AST constructors based on the code generator framework using the Blockly developer tool. The AST constructors return the ASTs as shown in Figure 19. The tool calls the constructor of an ECA block, each of which calls constructors for the event, condition, and action blocks. Constructors for custom blocks were implemented, which parse the completed ECA blocks and generate their ASTs. For example, Figure 24 shows that a constructor for an ECA block returns an AST for the ECA block consisting of event, condition, and action nodes. This study is notable for three features. First, the design of SmartBlock to be expressive enough to support IoT programming using the foundation of the IoT application calculus and building 54 out of 56 official sample smart apps using SmartBlock in an experiment. Second, the visual environment is extensible by compiling visual blocks into customizable Groovy code for smart apps. Third, SmartBlock provides a conflict prevention method that checks for redundancy, inconsistency, and circularity by automatically analyzing ECA blocks.